Hello, everybody, and welcome to episode 84 of the Hyperthesis podcast. I'm Liam.
I'm Pheely.
And I'm Patrick.
Today is the final episode of our 6th season, so exciting. I can't believe we made it this far. So what's our plan? We're gonna do this episode, we're gonna conclude the season, and we're gonna take a break for 1-2 months, something like that. Because
About that, one and a half. Well,
1.5 months.
Playing it by ear, maybe 2.
Yeah, because we've got the three of us are doing some traveling, so lots of work to do, lots of stuff to do, and it'll be nice to take a little break and then come back fresh with 2 months worth of physics prepared to talk about. So that'll be fun. Physics and environmental science, I guess.
And science in general, we'll say.
Yeah. So for this episode, however, our season finale, Pheely's gonna start us off with an intro topic, I believe, on a recent paper he published. Congratulations.
Thank you. Well, this is a long time coming. It's actually from my work in doing my master's, and we got a lot of results, and we got a lot of things to have to be fleshed out and discussed. And this is basically the first of the inception of my work in this field, in a sense. Because even though my group has published before in type of physics of design or statistical physics of design, I think this is the first one that has my name on it, or you don't count the code I published. So it's nice, to have something published finally after a lot of long work. And I think it's in a pretty decent journal, pretty nice. So
In Nature, right?
well, it's in a scientific report, which is a subjournal of Nature. It's nice that it's on nature.com though, so it looks like it's on Nature. Technically, it's part of Nature, right? And yeah, I'm really happy about it.
I'm just scrolling through it right now, and I like your figures and your diagrams. They're quite nice.
Yeah, I changed the color scheme to colorblind friendly too. That's one of the reviewers' comment.
Oh,
So I learned about colorblind color scheme. So the colors I use, most of it, I think the one that matters now are extinguishable by most or all colorblind people.
that's very good. I know with my publication, I actually had that thought when I was doing it. I was like, should I try and make this colorblind friendly? And eventually I gave up on it because it turns out I needed too many different colors. I needed all these crazy gradients of colors, and I kind of said, maybe it was the wrong thing to do, but in the future, I told myself I'm going to think about that more. But for my PhD, I'm not going to worry about it because I just need to publish and finish. I'm going to just get it done. And in the future, when I'm more established and have more time and maybe people know who I am a bit better, I'll do that kind of stuff more. But it's really good that you were able to do that. I'm a big fan of that kind of stuff.
Well, the thing is, we were using what the website called Color Brewer, which is basically creating a color palette that can be like distinctive, or that can be of similar color on a triad or something like that to create our color scheme, right? And they can only give not that many colors. So, and I didn't know it wasn't colorblind friendly either. And sometimes what I looked up for the colorblind friendly stuff, they only have a few colors.
So the title of your publication is called No Free Lunch for Avoiding Clustering Vulnerabilities in Distributed Systems. So what do you mean by no free lunch? Because that's kind of a fun little title.
Well, I guess we gotta skip the colorblind stuff and the...
I think we got the gist of it.
So the colorblind palette is called the Okabe Ito color palette. So they're the Japanese guys who studies these things, and they came up with the color scheme that works. So on their websites, basically, they're all articles about how to create colorblind friendly palettes and data visualization and stuff. So, well, if you want to look it up, Okabe is the name.
Or check out the description.
Yeah. So the no free lunch theorem is actually a more proper mathematical theorem, which we are not exactly referring to that specifically. There is there's a colloquial term, no free lunch, right? So whenever you get lunch, it's not free. You lose something. It might be your money, it might be your time, your effort. But in general, it's specifically for the no free lunch theorem, which we are not exactly referring to, is the idea that in optimization, there's no one one solution that fits all the requirements or fits all the situations. For example, you can find a solution, optimized solution for maybe how to get one place to another, right? And you said, oh, a straight line works all the time. It's the shortest path. Well, is it true if you have gravity, if you're, moving with on a slope, for example, you would realize that like the brachial strom would be, which is called, right? Brachial strom is the optimal solution there, even though you said, oh, the fastest way to get to 2 points is a straight line. That's one optimized solution, right? But it could be another situation where that's not the case. To put it more broadly, let you think of computer programs. You try to devise an algorithm to solve a problem, right? To find a solution. And then, oh, here's the most optimal stuff. But what if you perturb the solution a little bit? Then that's not, or perturb the problem a little bit, that's not true anymore. That's the idea of the no free lunch theorem. So I think these ideas been discussed a lot. It started by David Wolpert. I think he does like he's a physicist at the Santa Fe Institute. So he does computer scientist stuff too. Usually these no free lunch are used for like machine learning stuff too. Because now we have an idea that we're gonna come with a machine or like an algorithm that solve all situations, and there'll be free lunches, right? This black box that solve everything, but it turns out to be not true, and actually there's more like rigorous proof that was proven. This is a theorem, so it's not just a conjecture. It is a proper mathematical derived theorem.
Yeah, and as you said, it's very common in computer science. But I do just want to focus on the other part of your title and a main part, and that's the clustering that's going on within your within this paper and some of the vulnerabilities with it. So I think Liam has a question, but I definitely want to hear a little bit more about that and the specifics of like the clustering, because I see that you're using your naval architecture within this. But yeah, just if you can go into more details about that, of course, after Liam.
Well, mine's not a question. Mine's more so a comment on that maybe could answer your question. So we first talked about this subject, Pheely, way back in the day when we started this podcast. You were the our third episode, I believe, which is titled "Gutting Warships with Statistical Physics," was published on June 3rd, 2022, and this paper was published on June 4th, 2024. So about 2 years later, which tells you the kind of like detail and understanding you need to have of this stuff to publish it. So I for anyone listening, might be interesting to go listen to our third episode, which is probably a lot more rough around the edges than this episode because we were new to it at the time. And hear what Pheely says about his work there, and then listening to this episode, hearing him talk about it here, that'd be kind of interesting. See what 2 years of learning and experience can get you.
Well, the thing is, the data was done then. It wasn't a matter of like collecting or analyzing the data exactly. It's a matter of fitting the concepts and the data into understandable format. Because there's a lot of some like if you look, well, you hear the title, it's not something exactly relatable, or some would argue that's not really physical even.
Yeah, so maybe that third episode in 2022 answers your question, Patrick, but in case not, I'll let Pheely address it. So, what is the clustering, I guess?
Well, the idea, so I'm gonna say that the no free lunch we refer to is more colloquial term when someone just like, and everybody talk around say, hey, there's no free lunch for this. I'm not talking about machine learning or optimization in that sense. I was talking that, well, clustering is, imagine you designed like a system, like a little ship or a car, right? Clustering would be like you put your engine and the axle and everything, or the cooling system, the AC together, right? It's gonna cluster into one spatial place, and that creates vulnerability. Imagine, well, if you got hit, that car got hit, or in our case, we use example in naval engineering, so shipbuilding, let's say warships or any ship. So if you have components that cluster, well, what if you get shot there? What if there's damage there? Well, that's gonna be really, really dangerous for the entire system, as it could cascade and have like cascading failures to the entire system, or it really not just in ship design is also like airline networks, for example, where what if there are clusters in the nodes where people fly in that create a traffic jam, for example, or microprocessors, right? If you have the units, elements that be used a lot near each other, it's going to create hotspots, which could lower the performance of the entire system, basically. So now the problem is when you're trying to design or to optimize to create a new design, well, you want to avoid clustering, right? So maybe you want to spread things apart, but sometimes you want certain things to be close. So are there really a cost for avoiding clustering? That's one of the probably the main research question we want to answer. And we try to answer that. Well, we answered that by using statistical physics to not just explore an optimal solution, but also a suboptimal solution and all other solutions in the space, and see what are the determining factors that really shape the structures of the system, or shape the understanding of like, well, where does cluster come from? Does it come from these requirements in design that are conflicting each other? That's why the clustering happens, or are there any deeper understanding you can have? And the thing about the tools in physics is quite intuitive that we can use, like the concept of entropy or the concept of trade-offs between different degrees of freedom or free energies. So if we can adapt that into the design situations, we can get some insights as to how this clustering manifests and what happens if we try to avoid it. If we try to put things in certain place, does it really change the entropy, and what kind of concept we can derive from that? Well, the long story short is that we can basically draw analogies to polymer physics into what we call configurational and conformational entropy. So this, I think, is I'm getting a little bit over the top of people head, but the point is we can draw analogies to what systems we understand in conventional physics to try to understand why clustering happen. And it turns out there's always a cost when you try to avoid clustering. So there's no free lunch, because the cost is that the design, there's a lot of variability in design if you try to avoid clustering. So you won't know exactly where to place your components, and that could be good or bad things. But what we can inform the designer is that, well, there's a way to avoid clustering is to go to these what we call the high variability solutions. But may not be good when you try to determine the cost or whatnot, because you don't know exactly where they are. So that's the gist of it. I think I expounded quite a bit, but
Well, for those who are truly interested, they can go read your paper. And I said the title of it already, and we said what journal it was in, so you can just Google the title and it'll be the first thing that pops up, probably.
yeah, one thing I'm gonna say too is that network theory or network theoretic approaches has been done a lot, and there are a lot of network people who who have done similar things with design and how networks are connected. But one thing that we do differently is we incorporate the physical realization too. So it's not just you know nodes floating in some abstract space, because we understand that we talk with the naval architecture people or naval engineering people, see what's really the requirements in design, in practical design, and try to accommodate that too. So for example, it's like the warship takes sometimes 10 years to build, right? And in the past 10 years, technology evolved a lot. However, the ship was designed 10 years ago. Well, was it designed to be retrofitted with new technologies? So the time frame on technological advances is shorter than the time frame of research, procurement, development, and building. So, well, it's designed. Can the optimization algorithm then work? Is it really an optimization problem? So there's a lot more issues we can talk about. And well, we are thinking of doing another paper to discuss certain things on these design aspects and optimization. But this is basically try to um, build a foundation for it. We have an other papers that on this kind of like design problems and statistical physics. So this basically adding on to the foundation of what we try to build the understanding, the conceptual understanding of design problems. And we want to argue that, well, maybe it's not just optimization. It's not that obvious of optimization. It's only optimization, because there are practical aspects and practical concerns and issues that come up during your design phase.
Well, thank you very much for that, Pheely. It's going to be interesting to see what this leads to in the future. But for now, we should get on to our main topic, which Patrick is going to lead us through today. So, Patrick, you're going to tell us about, well, not tell us, but we're going to have a discussion regarding, I don't know if I want to say the scientific method, but just kind of how science is done. And I mean, we've talked about this before a whole bunch, but somehow this is different. So you can tell us how.
Yeah, so we have talked about the scientific method, and we've had many people on the show, and we've talked ourselves about how research is done and what types of research they're doing. But I thought it would be fun to take a step back from that and look at the questions that we ask ourselves when we're doing research. And just as a bit of background, this was spurred by some conversations that I've had with my supervisor, and really delving into, I would say, partially the philosophy of the scientific method and why we do science, and just questions around how we know what to ask ourselves, so how we can find where gaps are in knowledge within different scientific fields, and also just uh, other questions. So I kind of wanted this to be not quite an interview thing, but just kind of almost like a panel thing where I have some questions lined up where we can ask, okay, what about this as it relates to how science is done and what we all think about when we're actually trying to come up with ideas. So, of course, Pheely just published his paper, which we talked about, and how those ideas are actually produced, where you're looking for the gaps, and recognizing what's been done before and what can be done in the future. And so this is all, I would say, within the scientific method. But as students, especially in high school or even elementary school, you're taught that you first need to have a question. Then from that question, you can form a hypothesis, and sometimes it's a null hypothesis. Then you experiment somehow to get data to answer that question. You analyze that data and produce conclusions. But it's very interesting because we are in three very separate fields. And for example, for theoretical physics, you can't really do experiments. You do something else. So I want to delve into that and just how that kind of basic scientific method is different for everyone, and it's different depending on what you study.
Well, I think one thing I want to point out first is that scientific methods is different from just logical reasoning. For example, well, when you can find like correlation and such, and you in logic, right? You find cause and effect, and you kind of assume, oh, if A then B, or if not A then B, or not B, all these stuff. Like if an event happen, can you find a cause for it, and can you find some kind of correlation or relationship between them, and you can make basically a logical, what do you call it, deduction or argument that things happen because of what. But scientific methods, that we try to be more precise and to be more careful on making those correlation or like asserting that causation. So scientific method is like a method to be more cautious and be more careful about what we can draw correlation to. And what Patrick said about hypothesis and experimentation, those are basically tools that allows us to do that.
So that's really great that you brought up correlation and causation, because I find, especially for a lot of kind of pop science things or people who don't do research but still like are interested in science, that tends to get confused a lot. And there's this really great example that I learned a few years ago, but it's a good example for differentiating between correlation and causation. So, for example, if the weather is very sunny, it's middle of the northern hemisphere summer, it's very hot, then because of that, one, you might say eat ice cream or get a slushy or Slurpee or whatever they're called, whatever region you're in, but like a nice cold drink you're going to drink. Another thing that might be caused by a super sunny day is that you get sunburned. I know I get sunburned sometimes if I'm lazy with sunscreen. And so those are both causes of sunny weather, is that you'll eat ice cream or have a cold drink, and you'll also get sunburned possibly. But if you were to look at just, say, the relationship between eating ice cream and getting sunburned, you might find a correlation between them, but one isn't causing the other. So they're related, but one isn't causing the other. It's just correlated.
Yeah, and there's a big confusion sometimes with what is necessary condition and sufficient condition, right? So necessary condition is the something must be there. Well, it's something that must be there, the condition that must be there for the event to happen. But sufficient condition is all the requirements that for this thing, for the event to happen. So, for example, if you have a car, right, a necessary condition for a car would be to have gas, to have gasoline in it. But if you say I have gasoline in a car, well, maybe your car won't run. It's necessary for your car to have gasoline, but it's also necessary to have other things, right? Well, it's for the car to run sufficient. There are sufficient things that maybe like you need motor oil, you need the wheels, right? You need a bunch of wheels, you need frame, you need engine, for example. So all those together constitutes a sufficient condition for the car to run. But like for example, engine is a necessary condition, but so not it's not sufficient. You also need gas. So sufficient is basically bigger.
And I mean, segueing into kind of a first question and about the scientific method is to actually kind of do your own unique research, you need a hypothesis, much like a car needs wheels and an engine. And so that leads me to my first question, and this is great for the both of you, is what is the difference between a theory and a hypothesis? And do you need a hypothesis to come up with a theory?
Well, you don't need to prove a hypothesis, right? You can just it's a guess, it's a conjecture in a sense. Well, but it's an educated guess. Oh, yeah, educated guess, not guessed. Educated guess. So basically, theorem is basically proven, has some evidence to it. That's why we call theorem, or it has some logical proof. But hypothesis, like, well, I guess it rains because there are clouds. Because I guess clouds make it rain. And then you can prove that hypothesis by evidence or scientific method to make it a theorem.
Yeah, I mean, maybe the way I think about it, and maybe it's for all those people who care about semantics and technical details, it's not correct, but I don't care about any of that. So The way I think of a theory is like it's a model. Stuff happens in nature, and you have a hypothesis. So you think like, okay, maybe this is why this thing happens in our universe. So then you come up with some basic assumptions. You say, like, I want to create a model that, or at least for my stuff, it's like all math, right? So you want to come up with some math that matches reality. But the world's really complicated. So there's a lot of things to worry about, right? So you can come up with like a basic some assumptions. So if I'm way up in space and I look down on the Earth, a cow looks like a little dot. So I can assume that cow is a point particle or a sphere or something. It's the big joke in physics is a spherical cow. Cows aren't spherical, but when you're really far away from them, a sphere is a pretty good approximation. So that's my basic assumption will be, okay, a cow is a sphere. And then you come up, you have this assumption, and then you say, all right, I need some math to describe how the cow behaves. So, if the cow jumps off a cliff, Newton's law is probably going to describe its motion. Um, and then you have that math, and then you solve it, and you get a solution or a trajectory of the cow as it jumps off a cliff, and then you test it and see if it matches the experiment. And if it does match the experiment, then your theory is that, that's your theory is that there's gravity, the cow's a sphere, the math pretty much matches the experiment pretty well. And there's your model. The spherical cow is a model. I don't quite know what I'm saying. I'm getting kind of like caught in my own words, but in my mind, like a theory is a model. It's something that models reality, and it's a good approximation in some kind of regime. But if you zoom in really close or zoom out very far, maybe it fails, and you need a better model, so a better theory, right? It's like Newton's law is really good, but when you zoom in on like very tiny particles like atoms and things, it fails, and you need an improved theory. So then there's the quantum mechanics is a theory, and it turns out that theory fails in other regimes. So a theory is just a way to model reality, as far as I'm concerned.
I find that this is a very modern understanding, a modern way of thinking about theory. Because I think back in the day, so I can't assume because I wasn't alive. But if you think that 100, 200 years ago, those theory are, I think, believed to be more like a true description of reality. Like, oh, this is how gravity works. This is the law. That's why there were a lot of those, oh, Newton's laws, right? So they were exactly, oh, this is how the physical reality work. And now that we have more evidence that things contradict each other a lot, it becomes, so maybe it is not exactly laws. There are models that we think that describe reality, but there are flaws because all models are wrong, right? They only exist or they are only true in a specific parameters or parameter space that we set. Like, well, or like what scale, what is the magnitude of force. So maybe the force is too strong, your law doesn't work there, or the force is too weak, your law doesn't work there. And it becomes like, well, maybe you have a bunch of models that describe different natural phenomena, like standard model. It's called model for a reason, right? We still see contradictions in standard models, or like from the evidence we find in the super collider and stuff all the time.
Yeah, like I guess back in the day, people were like, "Oh, we figured out gravity. Surely it works perfectly, and it's like the law of nature." But then, yeah, like you say, you realize sometimes it doesn't work, and every theory we have, we've come to realize it doesn't work in some regime. But the other thing is that they only work in some regimes. I kind of forgot the point I was going to make. I'll come back to it. I'll remember it, I'm sure.
I really like that statement that theories are just models because I mean, talking to even people who do computer simulations and computer models, such as Taya, who we had on a little while ago, talking about modeling the ocean and the atmosphere and sea ice interactions with the ocean in kind of the North Atlantic. And she said that models uh, describe things to a certain point, but all models are estimations. You can't include everything. That would take way too much computation and might even be probably impossible, especially for chaotic systems like the atmosphere. So saying that theories are models and knowing that models can't model everything, they're just simplifications of some sort I think that's a really good observation and statement.
Yeah, scientists and physicists and mathematicians quickly realize that you can't do like 99% of math because it's just difficult, right? Like for quantum mechanics, you can only mathematically describe a hydrogen atom, which is like the simplest atom. The moment you start moving up a helium atom, that's an extra electron and an extra proton and extra neutron, it's like, oh, well, now the math is too hard to even solve that equation. And now what happens if you're talking about, Avogadro's number of particles, like 10 to the power of 23, this massive number of particles? It's like you can't perfectly describe everything. The math is just inconceivably hard. So then you come up with approximations. So, like density functional theory, it's a theory, but it's a bunch of approximations about how to describe something and model it. But I remember what I wanted to say is that even like our best theories, like we don't physically understand a lot of them. Like what is a wave function? It's a wave of probability, and then it collapses when you look at it. Like people still haven't agreed or decided what quantum mechanics physically really even is, and same with general relativity. They're both the theory of quantum mechanics, the theory of general relativity. What is space-time? It's this curve. What is curved space-time, right? Like we can't see it, but it seems to perfectly model, well, not perfectly, because it models whatever GR models very well. So quantum gravity we're still working on, as I always say, but yeah, they're all theories, right? You could always argue that, well, at least so far, currently we can always argue that you can go deeper and realize that maybe, curved space-time is actually just kind of like a macroscopic manifestation of some other thing, or like the wave function, probability waves are just some, um, the Schrodinger, like quantum mechanics is just some manifestation of like quantum field theory. Quantum field theory is like the bigger picture behind it. So there's all these layers to it, and some people think that there is a true theory, like a law of the universe where everything has like a perfect understanding, and some people think we'll never get there. And I'm kind of on the we'll never get there page because the universe is so complicated that I don't think we can ever fully understand it, but I think we can get close. We can we can asymptotically get close to the answer, maybe.
Well, one thing I want to maybe, I don't know if you disagree. I'll disagree with your choice of word. Because I don't think it's, you said hard, right? The math is too hard. No, I don't think that's the case. Because, well, when you say hard, I think I don't know if you mean complexity, but because, for example, multiplying a matrix, right? Two matrices are easy. But what if there are like 100,000 elements in the matrix? Well, you call that hard? Well,
Yeah.
right? So I think there's a little finicky there.
Oh, okay.
Because like when you have 10 to the 23 number of particles, well, if you do a molecular dynamics simulation, for example, right? The rules is not that hard. You can use computer to calculate each interaction. What makes it quote unquote hard is the order of magnitude of the number of particles. To me, it's not exactly that the theory is too complicated. It's just that we cannot practically calculate what's going to happen. So it's not a matter um of what do you call it, the depth in each interaction. Well, while there are depth in interactions, in complicated interactions, but when you add number of interacting elements to it, like three body problem, we don't even have a closed form solution, right? And if you put it to 10, 100, like approximation has to come in. But I don't know if I would describe it as hard.
Well, when I say hard, I just mean like you can't do it. It's like, right, and some of it's just like a numbers game, right? Like, in principle you know what to do. It's just you don't have enough time in the universe or processing power to do it. But some of it is just hard because, like, some systems, you have a second order differential equation. All right, you can solve that. Make it a third order. Okay, it's doable. And then you get a fourth order differential equation. It's just like we have no known solution to it. Like we just haven't been able to solve it yet. So you have to be clever and do approximations and things, and then it's a theory. It's not like a perfect description, and so some of it's hard, some of it's just a numbers game. We don't have unlimited resources. That's kind of my take on it, I guess.
Um, and just in terms of like hard and complex, an example is the 3D Ising model. So I remember we watched a talk many years ago from a math professor at St. FX, Keith DeBell, but he was talking about different Ising models and saying that the three-dimensional Ising model, if we were to try and compute it, a solution may very well exist, but would take a computer the size of the universe to actually compute that based on our current knowledge of computation. And so that would be, it's incredibly complex in the fact that you need such a powerful computer, which is in essence impossible to make, is hard. It's hard to do, if not impossible.
Well, I think you have to be careful there because numerical solution 3D icing model is really easy to obtain. You can do that on your computer. Like we did that in class for the high performance computing.
I mean, numerical solution, yes, but an actual analytical solution, no.
Yeah, for if you want to devise a computer algebra system like Mathematica for Maple to solve for the analytical solution, then I think someone did a calculation on it that the amount of what do you call it, the resources required would exceed the some limit that you can never get it. But the interaction itself are quite simple, right? It's just interaction between spins and is described by like a few terms. So in itself, the interactions are not complicated. Again, the complication from the curse of dimensions, more dimensions. You have many more computation to do, or many more terms to account for. I think it's go up by to the end, right?
And even then, like, the icing model is a very idealized system, and in a realistic system, you'd have more than just nearest neighbor interactions. Typically, you might have next nearest neighbor and blah blah blah. So like things just get exponentially more complicated, which I always think of theories as models, and again, maybe there's some semantics you could argue there, but for my purposes, that's kind of like what I think of them as.
So moving away from models and simulations and theories and what exactly they are, going back to like developing hypotheses and asking questions. Note that not hypertheses, but hypotheses. How do you actually start on a problem? So, especially again from our different backgrounds, what are your thoughts and processes that lead you to start asking those questions, to then developing those hypotheses?
I feel like this is super dependent on what you do and the way you think and all this stuff. But I've had some ideas in my life about different areas of research I want to pursue, and so my hypotheses are very much like I look at something and it looks like something else I know about. So, I see some math and I'm like, oh, that kind of looks like my project now. It's like the mathematics of it looks kind of like the mathematics that describes rainbows, or maybe it's my old project. I don't know what to call it anymore. But so the idea was like, oh, the mathematics of rainbows is this well understood thing. Blah blah blah, and then you do this kind of like black hole stuff and you see math that looks like pretty close but slightly different, and it's like, oh, okay, so my hypothesis is that somehow this theory of rainbows and stuff is related to the theory of Hawking radiation, and then so that's like the educated guess. And there's more ways to do it. Like I've had other ideas where there's one time, what was I doing? I talked about this in another episode before, but like I read a lot of these niche papers where people study kind of funny phenomenon. We had like, a breakfast physics episode, the physics of breakfast, right? And I was walking down the street and I saw some like salt stains on the road because it's Canada and you salt the road when it's icy in winter. And the way the salt stains, they left these like patterns, and I was like, oh, these patterns kind of look like the coffee mug patterns that happens when you spill coffee around a mug. So like I bet, I'm gonna guess that like the same phenomena is happening there. And what do you know? You go and if I was a real scientist, I would have went and built an experiment to prove that or show it or learn about it. But I just, Googled it and someone already done that and had the answer for me. So the way I come up with my hypotheses is typically like I notice some connection about something I already know, and then I go I say, I bet there's something's going on here, and then you go investigate it and see if you're right or wrong.
I'll put something similar too, but I think the keyword here is educated guess. Educated guess, not guest. But educated is, I think, the most important part. Because when I say you start on a project, you don't make hypotheses. You just can't. You barely know anything about it. I think the first thing you do is go read about it, right? You go read the literature that's around it. You go talk to people who do the research, or you talk to your supervisor, or someone who knows stuff about it. So that you can have an idea about what that phenomenon is before you can form a hypothesis, or you will go see the phenomenon, right? So in that sense, the most important part to form hypothesis is to get yourself educated, and then you project yourself into it, right? So you put your ideas into it, like, well, maybe it works this way. Maybe you base it on something you know, or the theory that you know. So what I do is basically think about like what I know, what can I relate to, until, oh, have I seen this type of correlation before? It's some theory that describes something similar, or maybe something that's so very different that, or the opposite, so we can form some kind of chimera out of these different ideas. And perhaps there's something new. Maybe you have a slight enlightenment come out that's, oh, maybe it works this way. But most of the time, those ideas are not very original, because a lot of times what you think of had been thought of before. So one important part is to make sure that those ideas are totally yours, right? You look it up, like, oh, well, has this been done before, or has this idea, these concepts been thought about before? So, and the internet is great resource, right? Or you talk to people in the field, and the odds are it's very likely that what you think is quite common, or people have thought of these solutions before. So, and then you collect them together, and you, as a foundation, and you build your hypothesis upon that. So I think this is more of a more advanced research stuff, because it's so complicated sometimes that if you start from nothing, unless you have a great enlightenment, you might not have any idea how to approach or how to build a consistent theory that has to be consistent with the rest of the literature, or most of the literature. You can contradict a bunch of them, but not all of them.
Yeah, I'm glad you said that, because that's what I was going to say as well, is that I was saying that, my hypotheses, it might be from all these connections I noticed, but sometimes you're just interested in something you know nothing about. You could look at something, you could see like you could look up at the stars and see a star twinkling, and you might be like, why is that happening? And now you have to go educate yourself on, like, the atmosphere and stars and light and all this stuff, and then you can eventually make an educated guess onto, like, why is this happening. So like a lot of physics was just people were interested, they'd see something and they were like, why is this happening? And they had to go educate themselves on all the known information on that topic, and then come up with a hypothesis and see, like, okay, here's what people think happens, but it doesn't quite work, so like, here's my improvement to it. And then they figured things out eventually over many generations of people.
Yeah, and I think educating yourself is, one, becoming increasingly easy, because you can just type into Google and you can ask Google questions now and be like, hey, how does this work? And of course, as you move further and further into a field of research, that becomes less likely that you'll find an answer, but you can start to ask questions that are adjacent to what you're trying to find, to try and see what's being done. But an issue with that as well is that there are more and more publications actually being produced, and more peer-reviewed publications. If you want to learn more about that, you can listen to our episode on it. But there's so much more information that there are actually programs now that are able to help you kind of organize everything to understand what's being done. And especially from an experimental perspective, and also from an environmental sciences perspective, there's so many different regions on Earth that you can apply different methodologies to. Um, and so it becomes tricky to see, okay, what's been done before? Where has it been done? Why was it done? And again, you can have thousands of publications relating to it. So there are, especially with AI, there are increasingly useful tools that are used to kind of parse through everything to help you figure out, okay, has this been done before? What hasn't been done before? And finding where gaps are within the literature. And that's something that was really been driven into me the past couple of years is finding gaps. So saying, okay, this question wasn't answered, or these different questions were answered about a certain thing, but this very particular question I have wasn't answered. So that's kind of a gap in the knowledge of mankind, we'll say.
Well, I would say this extends beyond science too, because I think this is just research nature in general. Well, it doesn't have to be science, right? Because you can think of philosophy has to be the same thing. You think about ideas and you're like, well, maybe this idea has been thought out before. So you basically go through this process of verifying your ideas and information you are well, I mean, your models basically, you're making your guess and your models, and you try to make sure that other people hasn't thought of it before, which is very, very difficult. Our human history is quite lengthy.
Yeah. Me and Duncan and one of Duncan's new master students are actually we have this project, and it's a project I've worked on for a little while now with some undergrads, and I have all these ideas for it, and Duncan's at this conference in Texas, and what do you know? Someone gives a talk doing like pretty much the same project, like on their own independently. So now we're talking to them because we accidentally kind of did the same project at the same time, across the world. So there, people are very quick to pick out these gaps in the literature, and like the approach they're taking is different than ours, and we have some unique stuff and they have some unique stuff. So it's good to like that's one of the benefits of the internet is that you can really communicate with people across the world and figure out who's doing what fast. Whereas a long time ago, you had to really um there's all these phenomenon physics named after multiple people because they kind of derive the same thing at the same time across the world without realizing it. Whereas that's it's still common now, but I think the people catch on very quickly. Like people will realize like, oh, like this other guy's doing it. I heard him give a talk on YouTube about it. So like now I can email or phone call him and we can collaborate on it. So that's always very nice about modern day science, I find.
Yeah, I take a little detour. I was thinking about internet the other night, or what internet actually does, or what it actually is. I think it is a method or a tool to help us basically allow us to find each other. So well, just go with me for a second, all right? But because before, if you want to you know reach someone, if they're far, you can do this like you have to know their address to send a letter to them, or you have a phone number, which is also a type of address, right? But and also come from the infrastructure that allows us to telecommunicate. And internet is basically a huge address book that you put your name in it, or you put your some type of address in it, IPv4, IPv6, right? It's allow us to find each other like anywhere in the world or anywhere when you have connections. And the thing is, with now that we can find anyone, well, not anyone, but as practically almost anyone, you can collaborate with them. You can share idea. You can exchange idea. If you think of the old early internet, right, with webboards, forums. So that was the main thing. It wasn't about sharing pictures or what we see in what we have now, right? Because you see a lot more of little forums that people just come out share ideas because it is basically a medium where you can put whatever you think on it. It can be very bad or it can be very good, but it allows us to find each other wherever we are. and that I think influenced the world tremendously, not just science. But if we talk about science, it's allow us to find ideas. We have most journals are all on the internet. I would claim that like almost all journals, scientific journals, are on the internet because that's where we keep our addresses and keep our records of our mind. So now it's become, well, even though I mean day to day life is might not feel like it, but you think about it, all the ideas you share now are on the internet and allows other people to find it, analyze it, agree or disagree.
Yeah, exactly. It's a very powerful creation for science, for sure. Patrick, I'm not sure if you wanted us to talk about. I kind of wanted to talk about um like what my typical process is for doing theoretical physics. So maybe it doesn't apply to every theoretical physicist, but my typical kind of routine. So my typical process is you start with a hypothesis, right? So you notice something you're interested in, you educate yourself on it, or you notice a connection, and then you come up with a hypothesis. You say, okay, there's some connection here, or maybe this is what's describing the system. Like, if I drop an apple, something's pulling it down, or something's pushing it down, one or the two, right? So you come up with a hypothesis, and then you make some basic assumptions. You say, okay, I have an apple, um, it falls down, so something's pulling it, and there's a medium, there's air, so maybe there's some wind resistance pushing it the other way. You come up with a minimal model, and you don't really care about the exact shape of the apple, so you approximate it's a sphere as well, or like a small point particle. You come up with, I mean, Michael Berry, this famous physicist, he likes to call these things minimal models, where you try and keep all the key elements to describe what you're interested in and ignoring the rest. But you can't keep everything or else it becomes overcomplicated, but you can't get rid of everything or else you miss out on the essential like science or physics of it. So you want this minimal model, you want the least amount of stuff as possible without losing the kind of essence of it. So you develop that, you figure out what your assumptions are and the system you're interested in, and then typically you get some kind of you try and get some math from that. So you say, okay, Newton's law describes how things move, and maybe deriving Newton's law is a whole process, but if you know it exists, it's very nice. Or in quantum mechanics, you know that the Schrodinger equation exists. So you take some differential equation and you plug these assumptions into it, and it'll give you kind of a specific equation. And in principle, that equation perfectly describes your minimal model, or your theory, I guess. But a lot of the time, that equation is really hard to solve. So maybe you can exactly solve it if you're lucky, but maybe you can't. So now you have to be clever and come up with clever approximations that kind of fit within these assumptions you've made, without kind of straying too far from the physics. So you say like, okay, if this apple is pretty small, we can approximate that it has a small mass relative to the Earth pull on it or something. Or you could say, if we're dropping it from very high in the sky, we can approximate that a lot of time has passed. There's all kinds of approximations you can make depending on your system. If it's in quantum mechanics, you can usually assume that anything with a Planck's constant in front of it is small, because the Planck's constant is a very tiny unit of quantum mechanics. There's all kinds of approximations you can make if you can't exactly mathematically model this equation. So then you solve your equation approximately or exactly, and you get some solution that should give you physical parameters. So, for example, if I'm solving like Newton's law, I could calculate like what is the position of this apple as it falls as time changes, and then you take that expression and you look at it and compare it to what an experiment gives you, and you should get two kind of plots, two different lines that kind of match up together or approximately match up. And that's kind of like, for me at least, and I know a lot of theoretical physicists, that's kind of the process. You come up with an idea, you come up with a model for it, you get some mathematics from that model, you solve that mathematics approximately or exactly, and then you match it to an experiment and see if it works. And if it works, then you've come up with a theory for this experiment. or for this particular thing that happens in nature. And if it doesn't work, it means your model's crap and missing something, or it means the experiment's missing something that the model needed. Depending who you ask and depending on the situation, it could be either or. So that's kind of my theoretical physics process of doing science.
I think mine is maybe similar but also different because computational work, your hypothesis evolve, right? Basically, because you can test your hypothesis quite quickly. Well, sometimes not quick, but it's definitely quicker than doing like a physical experiment because I can put it in a computer. It's like, well, what if this condition, what does it look like? Maybe if the result is different from what I have guessed in my head, and then I would amend my guess. Or well, before I amend my guess, I would look at the code. Like, well, what did I make a mistake? Why didn't it behave like I think it should? And then if it really doesn't behave like I think it should, then maybe the hypothesis is incorrect. So you kind of, well, what could happen? What could I change for it to fit the phenomenon that happened? So phenomenon in the computer, in a simulation that mimics nature. But if even the simulations, in a sense, has to be somewhat consistent with some experimental evidence, can't just be some random computations that you do, right? So there's those back and forth of this kind of reciprocal relationship, this kind of almost like cyclical. You go back from hypothesis to computation, which is like quote unquote experiment, and you come back to hypothesis and you revise and revise that, and it becomes
Yeah,
theory eventually.
yeah, I forgot to mention that in my process. So normally you would do a numerical simulation in my process. So if you get an equation that you can't exactly solve, you would first probably try and numerically solve it and see if it matches the experiment, to make sure that your kind of key assumptions make sense. And then once you know that works, you'll start doing like these approximations or trying to come up with like a mathematical way to solve it instead of a simulation slash numerical approach. So you have all these layers, they're all like consistency checks. They should all work.
So, just since we're running out of time just a little bit, just one final question, and just give maybe 2-second answer, just quick answers. But have your thoughts about approaching the scientific method and actually coming up with research questions and doing research, how has that changed since you first started? So I know we all did research in our undergraduate degrees, and now we're all doing PhDs. So how has that changed?
I'm For me, it changed in the sense that I do a lot more consistency checks. So if I want to model something that's complicated, first I start by trying to model like the simplest version of it. It's like, if I want to understand, if I kick a soccer ball into the sky, um, it's moving in one direction and it's spinning and there's wind blowing against it. And if I want to model that with math, the first thing I'll do is just do it without spin and without wind. So then I have something that's just under the influence of gravity. And then maybe I'll add in like the effect of wind resistance and get that solution and check that in the limit where the wind resistance goes away, I get back the original just gravity part. And then you'll add in spin thirdly. And then so you get a final solution that has all these different things, but you kind of build up from the ground up. And as you're doing it, you always check that, like, if I remove spin in this case, does it reduce back to the same solution I had before I added it in? So I guess I want to say I'm a bit more careful, but not in like a way that makes things slower, I guess. Basically, you just want to like check to see if your common sense is verified as you go through trying to model something. I guess that's how it's changed for me, because in the past I would just, I'm like, oh, this really complicated system, I'm just going to try and directly solve an equation to model it, and it turns out it's really hard. And if you understand the easier cases, you have a much better chance of understanding the hard case.
I would say there are two ways that um, you solve a problem or you approach a problem. And I think one of them is very, very difficult and has used a little bit of luck. So I think what Liam was talking about is like to do it from bottom up. So basically, you find the simplest model, or well, some would call toy model, or like the simplest thing you could describe without a complication, and you add complications, like building a building, right? You start from the foundation and stuff, and then you try to arrive at some theory or something that's consistent with all your foundation. And that is a very important skill if you want to be a scientist. You have to be able to do that. But the second method, I think, is what is separate like an average person from a good scientist, is to be able to do it from top down, and which is extremely difficult because sometimes you don't even have that much information of what's going on, but you come up with a model that works. And it's like, how the heck does it happen? Look, I would want to point out the power of creativity. That in a sense, you have to be quite creative. Sometimes, like, you just see it, and even though it sounds like mythical, but it's real. It happens all the time, more in mathematics than in science. I would say that it's like they just see it's true, and that could come sometimes. That would come, and then you build your theory or like the supporting lemmas or evidence to support that, right? But sometimes that doesn't work either. You think that, I think it's really like this. This is a new way to think about it. I see is how it should work. But no, it doesn't work. But from time to time, but very rarely, you get that top down building of your theory, and it's wonderful. It's one of the greatest feeling when you figure it out without figuring out all the details, but you know how it works. And that's come from developing your intuition by doing this a lot. Maybe you have seen most of the literature. You have doused yourself into this barrel of knowledge enough that you can make this creative intuition that come out, and here's a solution, there it is. But that's very difficult to do, and it takes time. Maybe that's why you have to do PhDs for many years.
Yeah, it's you build up an intuition for things as well. That's something that I never had in the past, and now I have. Because all right, but we'll move on in a second. But just we were Pheely, when the paper we worked on with Dean, right? There was some calculation Dean was doing, and I remember he was struggling with it a bit, or we were working on it together, and he was talking to me about it, and I can't remember if he was stuck or if he wasn't sure. There was something going on. I looked at it, and I just somehow knew. I was like, oh, like, you just have to do this, and it'll give you something that looks like that. And he's like, how do you know that? I'm like, I've seen like a bunch of things that kind of look like this in the past, and although they were different, they're close enough that I can kind of you get that intuition. You're like, oh, if you do this approximation, like something like this will happen. So that's something I have now that I don't. But for the sake of time, I think we should move on. So thank you very much, Patrick, for asking those questions. Me and Pheely just talked a lot about our thoughts. We didn't really ask you, so we'll have to do that again one day from your point of view. Me and Pheely like to talk. Our 2-second answers were each like 4 minutes probably. So
like true scientists.
Yeah, true scientists. Don't know when to shut up. So that was a very good conversation. And before we get to our story, you're gonna tell people how they can reach us.
Absolutely. So this is the end of our season number 6, but we are excited already for season number 7, and we want to keep you updated when we will be launching our 7th season. And so the best way to see updates from us is through our Instagram. We can be found at the Hyperthesis. You can see updates there. Maybe Liam will post a meme or two over our break. And we'll certainly be letting you know when we'll be back on the air. Although I guess on the internet. If you are interested in being a guest next season, we would love to have you on. If you are an expert in your area, you can reach out to us over Instagram. You can just send us a DM. Again, that's at the Hyperthesis. Or you can send us an email. We are hyperthesispodcast@gmail.com. So you can send us your interests. You can send us comments, questions, concerns, or suggestions for topics. We are still planning out our season, and we really want to have a lot of guests and a lot of good discussion. So if you think you have an idea that's been burning a hole in your head of, oh, I really want them to talk about this, then please let us know. If you're listening to us, congratulations, you found us on whatever podcasting service you're using, whether that's Apple Podcast, YouTube Music, Audible. We are based out of Spotify. You can find all of our information there, but we are found pretty much wherever you get your podcasts. So feel free to give us a share, give us a rating if you are able to on your podcasting service, and leave a comment. We are always looking for feedback. Finally, we do have our YouTube channel where you can like, subscribe, comment, do whatever you do on YouTube. But you can also see for this season, we will, I suppose, transitioning next season to a different color scheme. But this season, we had this beautiful grayscale color scheme on the YouTube channel, which you can check out and watch all of our videos with mesmerizing graphics. So check us out, find us, send us a message wherever you can, and thank you for listening.
Thank you very much, Patrick. So today's story is going to be a pretty short one, and it's about the famous the famous physicist William Unruh, who we've talked about before many times, and I just wanted to talk about his journey in creating a branch of physics. So kind of the process he went through. So this field of analog gravity, which I study, which I've talked about again many times, but it's basically very short summaries that you make things in a lab that look like black holes, and you can learn about black holes that way, because black holes are too far away to actually experimentally investigate. And you can also use analog gravity to study inflation, because inflation only happened once and we weren't there. So if you want to understand it, you can make something that looks like inflation in a lab, in like a fluid or something, and then you can study, does it do what you think it might. Go listen to our other episodes about that. I don't know which ones they are, but they're somewhere. So William Unruh is a physicist. He was born in 1945. He's a Canadian physicist, and right now he works at the University of British Columbia. And I actually had the pleasure of meeting him twice at 2 different conferences. So that was fun. So he's famous for this thing called the Unruh effect in physics, where if if you accelerate very, very fast near the speed of light, you'll actually, as long as you continue accelerating with a constant acceleration, you'll start seeing particles appearing out of thin air. And that's related to the Hawking effect, but I won't get into that. So that's what he's most famous for. But he also created analog gravity. He came up with the idea that you could make things that mimic black holes. And this kind of came from, he told this story at his talk, so I'm paraphrasing it. I don't have this, maybe the story's written somewhere on the internet, but I'm just telling it from memory. Where he was a kind of a black hole guy, like a quantum gravity / general relativity physicist. So he had to give a public lecture in the 70s, I believe, about black holes. And black holes were something that were kind of a hot topic at the time, and he had to he had to explain to people who weren't physicists how black holes work. So that's kind of a hard thing to do. So he came up with this thought experiment about 2 fish in a river, which I think I might have told before, but I'll briefly tell it again. Imagine you have a river and it flows over a waterfall. Well, it becomes a waterfall by flowing down the side of a mountain or something. And you have 2 fish, and they're in the top part of the river. They can talk to each other, so they produce sound waves, and the sound waves can travel against the flow and upstream. So because the sound waves move faster than the river flows towards the waterfall. But if one of the fish falls over the waterfall, then his sound waves will actually be pulled down the waterfall faster than they can move up it. So the fish at the top will never hear him. So that's kind of like a black hole, but with sound waves. So a black hole, if you're outside a black hole, you can shoot light and it can go wherever you want. But if you're inside a black hole, any light or signal you produce, if you have a laser pointer, it won't actually escape the black hole. It gets pulled in faster, and that's why they're called black holes, because you can't see them because they don't actually reflect, or classically they don't reflect any light or emit any light. So that was his kind of thought experiment, where he's like, all right, this is like a black hole, but for sound waves. So instead of curved space-time, you have water in a waterfall, and instead of light traveling through the vacuum, you have sound waves traveling through the water. So he came up with that thought experiment to kind of describe it to the public, and it worked pretty well, I guess. And then years later, he was as physicists often are, or professors, they're often forced to teach a class they don't know very much about. So he was forced to teach a hydrodynamics class. And he was learning about the Navier-Stokes equations and how you can linearize it. You can do this process where you are able to describe small little excitations, small little waves on the back of a bigger body. So like imagine like a tiny ocean wave in the ocean. You can do a process in mathematically called linearizing where you can come up with some math to describe that. And this, I guess his hypothesis, he was like, oh, I wonder if I linearize the Navier-Stokes equations and I have some specific kind of flowing system, does this fish in the waterfall analogy actually look like a black hole? Is it not just a cute little idea? Is it mathematically rigorous? Do you get something that actually looks like a black hole? So by having to communicate to people, he was actually able to come up with this idea. So by having to, talk to the public about it and by having to teach students about it, he had this hypothesis that maybe if you do this, you get a black hole, you get the mathematics that's very similar to a black hole. So he did this in like a 1980s paper. I forget what year exactly, and I forget the title of the paper. But I think it was called like Sonic Black Hole Horizons, or maybe that's not the name of it. I don't know. I've read so many papers on this stuff that it all kind of blurs together. But he did this, and he found exactly that at this sonic horizon in the waterfall, you get it emits sound waves with a specific temperature, a Hawking temperature. So he actually found that this cute little thought experiment was mathematically a bit more rigorous, and that you get kind of Hawking radiation that black holes get, except you get it in a sonic black hole as well. So from that, the whole field of analog gravity stemmed, where you can use fluids to mimic curved space-times with quantum excitations on top of them. And it's my field now. So I just thought it was a very interesting kind of the process he took to get there was very much like, a lot of researchers don't like teaching and they don't like public outreach. They're just quite happy to sit in their office and do science all day. But without that, he wouldn't have created this field, which he's partially famous for. So that's not quite the story of Bill Unruh, but it's the story of how analog gravity was formed through him. Well, thanks everyone for listening. Thank you, Patrick and Pheely, for your main and intro topics, respectively. And thanks everyone for tuning in for our season finale. Like we said before, we'll be back in 1 to 2-ish months with some fresh people and some fresh topics. It'll be really fun. But until then, I'm not sure if Patrick, Pheely, you guys have anything you want to say before we finish?
Well, I'll see you guys later. Take care.
Bye, everyone.
Very good. Thanks for listening, and we'll see you next season.